All right. So the last talk of this session is on method bundles, and this is again by Dimi Racordon. Go ahead.
So hello again. I'm still Dimi, and I'm still a postdoc researcher at EPFL. And I'm still working on programming language design. I'm still working on high-low, and today I'm going to talk about another feature of the language that is about gathering various implementations of the same operation into a single entity. So why do we want to do that in the first place? Well, maybe we can talk about this Rust example for a little while. So here we are looking at a simple Rust function. It's called filter variable, and as the documentation suggests, it's a function that will take a set of candidates. You can imagine that's candidates of name resolution, for instance, and it will filter those that are viable according to some predicate. But it's not a very good implementation because, well, we don't want to pay for this needless copy. Here I'm creating an entire copy of all the candidates just to filter some that I don't want later. So I just copied a bunch of useless candidates here. So a better way to write this function would be to write it like that. Now I'm doing a filter that will just extract the candidate that I'm interested in and will copy them. And then I will gather all of these different candidates into a different set, and then I can report if something goes wrong. So this function is just better than the previous one. But what if I don't want to report the error anymore? Maybe I just want to filter the candidates and be done with it. Well, in that case, I should go back to the first version, the in-place filter. Why? Because now I can reuse the existing storage that I already had. I don't need to create a brand new set just to store the things that I'm interested in. So what we end up here is that we have a situation where we have one operation, essentially. There is a filter, but I have different implementations of these operations, and they have wildly different APIs. So you might say, well, it doesn't help because you choose Rust, right? Rust has an idiomatic way of expressing in-place things and copying algorithms in a very different style. But this is a problem that we can also encounter in other programming languages. So for instance, we have these differences in Scala or in Swift, and you can pick your language. I'm sure we can also find this issue. Usually the answer is to come up with some kind of naming convention. So for instance, in Scala, we would name functions operating in place with this in-place suffix that we just add to the function name. And in Swift, we would try to be even a little more clever and choose a different function name. But these naming conventions, they don't really scale, and also they are depending on the user knowing them in the first place. So this is not a very ideal situation. In the ideal world, what we want to do is to write one single declaration, filter, because this is the operation that I'm interested in, and then inside filter, it will do the right thing, depending on the caller's context. So this is what we are trying to achieve with high-low, which is still the language I'm working on. And well, in the previous presentation, we focused on the generic programming aspects, and this time we'll focus more on the efficiency aspect of the language. But before we go back to these method bundles, I think it's it's a bit important that we first focus on how high-low achieves its goal in terms of safety and efficiency. And the entire story here is based on mutable value semantics, or MVS for short. In the strictest form, MVS is a discipline that's about banning shared mutable references from the user model. So it's a programming language with no references whatsoever. So what we can do with this is similar to pure functional programming languages. But we still want to do part-wise in-place mutation. So we want to be able to do to mutate things in place. So here, for example, the first part of S, which is here representing a pair, can be mutated in place without reassigning the whole pair. That is in contrast with a functional update, which is what you would do in a more functional-oriented language. So for instance, here I picked Scala, where you would just reassign the whole pair to a brand new object. But if you do that, now you need to pay for the creation of a brand new object, where instead of using the existing storage that you had. And also note that the ampersand here is not the address of operator that we would have in C++. In Hilo, we need to mark mutation with this ampersand just for people to see that it might require more attention because mutation is happening here. So how do we achieve this MVS discipline in Hilo? Well, the perhaps most important feature of the language, it has a linear type system, meaning that values must be used exactly once. It's in contrast with a affine type system, like Rust, for instance, where values must be used at most once, but you can just forget values. So here, linearity makes this program illegal because we are using S twice. So the compiler will complain here that we cannot use S again. So an easy fix is to make an explicit copy here. And in Hilo, we need to make all the copies explicitly, so even for simple data types like integers. But this solution is not very user-friendly. No one wants to copy all of their integers everywhere. So we can use some observations to make that linearity a little simpler to use. The first is that we can relax a little the definition of using a value to make a distinction between just reading a value and consuming it. So if we only need to inspect the contents of a value, maybe because we want to print it, then we just need to read it. We don't need to consume it. And in Hilo, we can represent this lesser access with a let binding. So here, I'm saying that I want T to be able to read the contents of S, but not necessarily to consume its ownership. So what is consumption then? When in Hilo, value is consumed when it gets stored into storage, or when it's returned from a function, or when it is deinitialized. Deinitialization is typically inserted automatically. I say that Hilo is a linear type system, and we didn't see any consumption before, but this is because this deinitialization is inserted by the compiler, who is clever enough to understand where to put the deinit call. I could make it explicit, but otherwise the compiler will do it for me. So that means that, indeed, we do have a linear type system. It's just that most of the time I don't need to talk about deinitialization. But that is important because we can attach behavior to the initialization so that we can use resources. We can manage the resources as linear resources. So for instance, we can imagine that S is a vector. So it is handling some pointer to some out of line storage, and now we can implement the allocation of this storage automatically, like we would do in C++ or Rust, for instance. So at this point, you might say, well, are you just lying a little? T is as good as a reference, right? It's just in access. It looks like a pointer or reference. But the difference is that in Hilo, this doesn't have a different type. T has the exact same type as S, and so I don't need to think of it as a reference. I don't need to think about dereferencing operations. This is just an S, just a vec2 here. And the compiler will enforce the fact that I'm respecting the constraint that I placed on myself by saying that I will just read from this. So for instance, it's illegal here to modify S while T is extant because I said that T wanted to behave like it was a value, like an independent value. So if I try to sneak back T and modify S, then that would violate this assumption, and so the compiler will catch me. Lifetime are non-lexical, it's like in Rust, so swapping the two last statements fixed the issue. And we can create also write accesses that are like the let accesses, but they also let me modify the value. And then to modify the value, I need to have exclusive access. So now the fact that T has the right to modify its value add a constraint. Mutation always requires uniqueness, so swapping the two last statements is, again, illegal. So here the compiler will complain that because we promised that T could behave as though it has exclusive access, then trying to break this promise by reading it the value behind its back is as much as an error as the one that we had before. And well, all of these different accesses, we can also use them at function boundaries. So those can be those different keywords, let, in, out, that we've seen before. We can use them as passing conventions in functions. And so here, for instance, I can say that this function offset is taking its first parameter in, out, which is behaving exactly in the same way that we've seen before with just the local bindings. So to give a parameter to offset, here I need to make sure that it is unique, and then offset can pretend that it's a unique value on which it has ownership, at least for the time of its execution. So now how this relates with the method bundles and the problem that we've mentioned before? Well, we can use these conventions to define different variants of the same operation. And at call site, I can select which of the variant I want to use depending on the specific context I have at the call site. So here, for instance, I have all these different filters, filters in-out, filter sync that is consuming, and another filter that is copying its argument. And I could use filter sync if I know for a fact that I will not be using the argument anymore. And so if I do that, then I can rely on this implementation that will be more efficient in this case, because if I don't need the contents anymore, then I can maybe reuse the existing storage rather than using filter let, which will inevitably allocate new storage. But this is not good for ergonomics, right? This is not any progress on what we've had before. This is just another naming convention. I need to know about filter let, filter sync. All of these different filters have their specific documentation, and so this is still a burden for the user. So what we want to do is to create a bundle. We want to gather all of these different implementations under a single declaration. And now each of the implementations correspond to one specific variant of the operation filter that has one documentation and is just one entity. It's defined here as an extension because now it became a method accessed with the usual dot syntax that we could find in Java, Scala, Swift, you name it. So there are two main benefits of doing that. The first is that for the developers, we no longer have to come up with some kind of naming convention and stick with this naming convention. And for the users, well, we don't have to look for different pieces of documentation across and trying to understand all of their different implications. They are all here in one single declaration. But the second is that it's not just about documentation. Now we have an opportunity to teach the compiler about the relationship between these different variants, and so that means that the compiler could itself select what is the correct variant to use depending on the caller context. So it's no longer a burden on the user. The user can just write filter, because this is what the user wants to do, and then the compiler can decide what specific filter should be used depending on the unique situation at the call site. So for instance, here, the call to filter will use the in-out variant because this is the only one that makes sense to apply in this situation. We want to modify the filter, and we still need the receiver of the filter after the call. And so we need here to use the in-out version. But if we remove the error reporting, which corresponds to the situation that we had in the introduction, then the compiler would use the sync variant because now I don't need the value anymore. Okay, so, yeah, this is what I'm saying. So how does this magic work, right? How the compiler can guess? Well, to understand, we need to look a little into the compilation pipeline of Hilo, and specifically, we need to look at the IR. So Hilo is Hilo is going through the standard compilation pipeline, but then after we have type checked the AST, we are compiling down to a lower level representation where we are doing a bunch of different things, including here guessing what kind of variant you wanted to use. And IR generation itself is decomposed into a few steps. Here today I will only talk about the two first, but if you're interested, I had a talk last year at Iwako where I talked about the whole pipeline, or catch me at the coffee break. So Hilo IR is a statically is a typed static single assignment instruction set that is designed to express and check the flow-sensitive typing rules of Hilo, and it looks like a lot. It looks a lot like LLVM if you've ever used LLVM. So in Hilo IR, a program is a collection of functions and global constraints, and control flow is represented by unstructured branch statements. So for instance, here we have a fragment of the IR that corresponds to this function that we have on the left. And the fragment that we're interested in is the assignment of this binding T here. And I will walk you through the IR that we see. We can see that it looks a bit like assembly. So the semantics of the IR is defined in terms of a machine with an unbounded set of registers. Again, it's like LLVM. And those can be seen as the variables at the IR level. And they are assigned only once. So all these percent something, they are variables. You assign them once, and then this is the value that this thing will have for the entire function. So here, for example, %1 is a register that is containing the result of some sort of stack allocation. The stack allocation corresponds to the argument that will pass to the subscript of A. Here. And %8 here is another register that represents the result of binding T in the resource program. So this is the end of the call to the subscript that we have on the left. So values in the source language are typically represented by stack allocations, and the values of the integer that we use to subscript A is indeed stored on the stack here by this allocate. So this approach makes it convenient to check linearity, the linearity model, because the stack allocation is kind of a cell. So we put values in a cell, we remove values from the cell, and then the value that we put in the cell is just a linear resource, and I can track it. Now the cell is initialized once here because I put a value inside, and I can talk about the ownership of the value when it moves out of the cell. So for instance, when I insert the daynit call later here. Perhaps more surprising is the fact that in the IR we have some kind of ghost instructions, spooky, but this represents the way values are being accessed. So here, for example, there is this %3 here. This is called the access instruction in saying access set. What does it mean is that, well, if I want to store a value to %2, which is the a subfield of %1, which is the allocation, so basically a view into the allocation, I need to create this access, and that will give me the right to initialize it with a value. And on the other hand, %2 is just a raw access to the value. It doesn't have any capability. So every time I want to create, I want to perform an operation on some cell, I need to say what kind of permissions I want on this, and I can read, write, or initialize with the different accesses that we have. So now we are getting to the interesting part. A bundle is kind of defining multiple different possible executions at once. So we need to represent this inside the IR, and that is what we are doing here with this project bundle operation. So the bundle is simulating a call to different variants at once. And now it's the task of this specific IR path to determine which one of the bundle we want to do. And this path is called access reification. So we look at all the uses of the instructions, and we try to narrow it down to the specific access that we need. So in this case, we can guess that we need just a let access because there is no use of T that is mutating after the fact. And so we will reify this project model into, because here we are creating, so we are creating the different accesses. We will look at all of the different accesses that we will perform on this %8, and we will use it to reify it to a simple project with only the let access. And we do that by analyzing all the future uses of the %8 register that we have here. So this access reification, we can do it in a fixed points iteration until we have reified all the different variant bundle accesses that we had, and we end up with an IR that has only concrete accesses to every call. And so this is how we implement the magic. There's now, going back to the user level, you might think that it is a bit inconvenient to have to write all of these different variants. So I have good news. The compiler can synthesize some of them for you. So typically, you probably know the best way to implement all the different operations of your type, but maybe you don't care that much, or maybe there is not a specific gain to be earned by rewriting the implementation over and over. So what you could do instead is to have the compiler synthesize it for you. So for instance, if you provide a let and an in-out operation, then the compiler can figure out how to create the sync version, and it will generate this code automatically. And conversely, if you provide the let and the sig version, the compiler can provide the in-out version for you automatically. This is the code that will be generated for you. And so I could delete the in-out line here, and it will be as though I had an in-out variant inside. And this is based on the correspondence between a in-place update and a functional update, which is what we saw in the comparison of high-low and Scala in the beginning. So as takeaways, I would say that method bundles can be used to gather these different definitions that we have, and it relieves the user from a few burden. The burden to have to look for the different definitions, the burden to have to deal with different naming conventions that are often clunky and don't scale. And it also teaches the compiler about the relationship between your different implementations. Based on this knowledge, the compiler can then select the right implementation, and this is done in high-low through a data flow analysis at the IR level. Also, the compiler can synthesize the implementation, missing implementations from the ones that you have, exploiting the relationship that exists between pure functional programming and imperative programming. So the fact that an in-place update corresponds to a functional update. And again, all of that is implemented in high-low, so please check out high-low once again. And this is all I've got for you today, so thank you very much for your attention twice, and now I take your questions.
All right, we have plenty of time for questions.
Perhaps just as a precursor to a second question, the synthesis of the default implementations, is it relatively or absolutely uniquely determined a priori?
So, sorry, once again, I didn't...
I mean, those default implementations that you talked about, are they uniquely defined, or is it you know, is there some space for different versions?
So no, if you ask the compiler to synthesize, this is exactly what you will get.
I see.
Because there is a priori no clever way for the compiler to know how to make a more efficient implementation of this synthesized version. So yeah, of course, then you can provide your own, but if you synthesize, then this is what you get.
Then maybe a philosophical follow-up question that I already expected to ask. I mean, isn't this coupling of things that where one thing is sort of, you know, uniquely determined, isn't that a sign of some lack of abstraction?
In what sense?
Well, at the meta level, right? If you're writing programs where you expect to often have that situation where, you know, some part of the bundle should be synthesized, is there some better abstraction somewhere in reach here?
Maybe. The thing is more that I see this feature as a way to eliminate a lot of the boilerplates, because let's say we don't care about performance for a while, and you only define in-place operations for everything. It might be the case that you have a function, you just receive a set, and you want to return the set filtered. But you only have your in-place operations. So what you need to do now is to allocate some storage, you copy your set into your local clone, you do the in-place filter, and then you return. This is restatements that you don't want to write. You could just say, hey, these restatements are always the same every time I want to use my in-place filter in a functional way. So the synthesization is doing that for you. This is eliminating this boilerplate. Now, if you want to go a little deeper and say, yeah, but actually, rather than just doing the dumb thing, I could be a bit more clever and not copy needlessly some parts of my data structure, then you could go and write your own functional feature, and then you would have some gains.
Right, so maybe you pull it out of the compiler.
Pull it out of the compiler.
So right now, the synthesis of the default implementation is sort of ingrained into the compiler, right? So if you
Sure.
made it a proper abstraction, maybe you could pull it out of the compiler.
Yeah, then I would ask if it's not in the compiler and the user doesn't have to write it either, then where is it, right? there's just that many places between the source language and the compiled program. So maybe we can debate on what the compiler is, but at some point code generation will have to do it, right?
Just to have a bit more fun. So as Benoit was saying, there's only one time.
Yeah, sure, but I mean, it's any time you want in this compilation pipeline.
All right. Anyone else? Okay, so when I was looking at these bundles, just before you folded the 3 different versions together into a bundle, I saw different types for the different versions.
True.
So what's the type of a bundle?
That's a very good question, thank you. Where is it? I think it's here. Yeah. So, in particular, we can see that the in-out bundle has a different type as the others. But it's kind of obvious if you think about what the in-out thing is doing. So we named this modifier in-out because the way we can think of it at the function boundary is that you take some data in and then you will put some data out. And so clearly the translation of this is you could just take the data in with the sync variant, for instance, and return it. So the correspondence between the signatures here is kind of obvious. The in-out is just expressing the return type directly into the argument. So the bundle here works because the type of the bundle is the notional type of all of these operations. These are notionally all operations that take a candidate set, a predicate, and return a candidate set. But the way that we return the candidate set might either be on the return value, or it might be on just the value that we put in the out position of the in-out parameter.
Okay. We have time for one last question. So one more question that I have. When I look at these different functions, I'm thinking, can I annotate multiple arguments with one of these keywords of in-out, sync, and let?
An excellent other good question, and no, you can't. So this is a limitation of the method bundles. They only work, the variants can only happen on one receiver. If we had multiple dispatch, then we could apply this method. Although, to be fair, I'm not exactly sure how it would look. It just happens to work relatively okay with one single receiver.
All right, thank you. Let's thank the speaker again.
Thank you.